Good day everyone. In today's video, I'm going to discuss all about digital companding. So, companding is actually from the words compression and expansion because we do the compression at the transmitter side and expansion on the receiver side. And in the transmitter side, we first do the sampling, quantizing, encoding before we do the compression. So this is for the digital companding. Again, for digital companding, we do first the sampling, quantizing, and encoding because in analog companding, the compression comes first before the sampling. So that is the main difference between the digital companding and the analog companding at the transmitter side. While on the receiver side, we do first the expansion, then afterwards we decode the data. Then that's the time it is returned to an analog input signal. So let's have the digitally companded PCM system wherein the digital companding is very evident. So say for example, we have an analog input signal. It could be a voice, digital process, or data. Then it passes through a bandpass filter. So our bandpass filter limits the frequency of our analog signal. It only passes a certain frequency that is within its range. Next, our analog signal that passes through bandpass filter would pass now to a sample and hold circuit. So in our sample and hold circuit, our analog signal would be sampled, or we would get a sample of that certain say for example, we have an analog signal in this waveform. So we would get a sample of that waveform for a certain period of time. Then get another sample for a certain period of time until the next sampling happens. So the sampling that is used or evidently used here is the flat top sampling, wherein the top of our amplitude is actually a flat here. It is not a natural sampling wherein the original form of the amplitude is retained. So again, what is used here is the flat top sampling. So the output of our sample and hold circuit is actually a palm signal. Next, this palm signal or PAM signal passes through an analog to digital converter. So from analog signal, it would be converted digitally, and the output of our analog to digital converter is actually a linear parallel PCM code. So say for example, the commonly used is a 12-bit linear parallel PCM code. Then this 12-bit would pass through our compressor. This 12-bit would be digitally compressed, and it will now become an 8-bit code. This is only for example, because the 12-bit linear parallel PCM code and the 8-bit compressed code is the commonly used nowadays. Next, we have the parallel to serial converter. And at the receiver side, we have the serial to parallel converter. So this is the transmission medium. Next, we expand because from an 8-bit code, which is transmitted, it would now be expanded back to a 12-bit code. Then we have the digital to analog converter, wherein it converts our 12-bit linear parallel PCM code back to an analog signal. So we have the whole-in circuit and bandpass filter, and then our output now would be an analog signal form. So now we have this 8-bit code, and it comprises a sign bit. If ever we have 1, that means it is a positive value. If ever our sign bit is 0, that means it is a negative value. After the sign bit, we have the 7 bits remaining. The 3 bits is also called as the segment identifier. So it identifies which segment does that 8-bit code belongs, because our 8-bit code, or the 12-bit to 8-bit code, is actually resembles the mu255 analog companding, or for its graph, and it has 8 segments. And this 3-bit in the 8-bit segment, in the 8-bit code, is actually the segment identifier. Where does it belong? It could be segment 0, segment 1, until segment 7. Afterwards, we have our 4-bit quantization interval. So that is 4 bits that could be between 0000 until 1111. So now my focus would be how is the 12-bit code compressed into an 8-bit code. So this would be the steps. First, we have to transfer the sign bit to the 8-bit code. So we have to automatically copy the sign bit as stated here. Next, count the number of trailing zeros. So for our 12-bit code, we have the sign bit at the left side, the most left side, and the 11 bits are the magnitude of it. So from the most significant bit, we have to count the number of trailing zeros. Next, after counting the number of trailing zeros, we have to subtract that number into 7. And we must take note that this number must not be greater than 7. And that result must be converted to a 3-bit binary code, and that would be our segment identifier. Next, the next 4 bits after the 1 would be our quantization interval. And we must always take note that X bits positions are truncated during compression. So later on, I'm going to explain this further. And A, B, C, D are bits for quantization interval must be transmitted as is, and a sign bit which is also transmitted as is. So to fully understood those steps, let me give you an example. So say for example, we have a 12-bit code in this sequence. Now, based on the steps presented, it is stated that we must copy the sign bit. So first, let me present the binary codes as divided for us to easily answer it. First, we have this sign bit. Based on the steps, we must have the trailing zeros followed by 1, which is our indicator that is between the segment identifier and the quantization interval. So we must always assume that there is 1. Then we have the 4 bits for our quantization interval. Then the rest of the bits would be the truncated bits. So based on the steps, we must retain or copy the sign bit from the 12-bit code into an 8-bit code. So whatever is the sign bit, we must copy it. So since it is 1, we must copy 1. Next, count the number of trailing zeros. So this would be 1, 2, 3, 4, and 5. Then, after counting the number of trailing zeros, it is stated that we must subtract it from 7. So 7 minus 5, that is 2. After counting the number of trailing zeros, subtracting it from 7, we must convert this answer into a binary number. So 2, converting it to a binary number in a 3-bit binary number is equals to 0, 1, 0. So we have to put our answers here, 0, 1, 0. So we have now our 4 bits. Next, we have here the first occurrence of 1 that is between our unit identifier and the quantization interval. So we just have to assume the position of this 1 or just drop it, since in compression we must shorten our binary bit or lessen the bits that we have to use. So we have to sacrifice some bits. So that means we have to drop this 1 here. And later on, we have to assume that we have dropped this 1 so that we could return it afterwards. Then copy the next 4 bits, and that would be our quantization interval. So that would be 0, 1, 1, 0. So copy 0, 1, 1, 0. So now we have our 8-bit code from the 12-bit code. So we have 1, 0, 1, 0, 0, 1, 1, 0. Our 8-bit compressed code is 1, 0, 1, 0, 0, 1, 1, 0. Then, if we identify these parts, we have 1 as our sign bit. Then 0, 1, 0 is our segment identifier, which now belongs to segment 2, since this is our segment identifier and this number or binary code is equals to 2, so that is why it is in segment 2. Next, the 4 bits afterwards are the quantization interval. Since we are done with our digital compression from 12-bit code into 8-bit code, let's proceed now with our digital expansion, which is from 8-bit code to a 12-bit code. So we have the steps. Again, we have to return the sign bit or retain the sign bit, copy the sign bit. So that's just the same. Next, take the segment number. So whatever is the segment number, say for example 2, 1, we have to subtract it from 7. And whatever is the answer, that would be the number of zeros we have to add up. Afterwards, we have to reinsert 1, since in compression, we have assumed the position of 1 that is between the quantization interval and the segment identifier. So we have to reinsert 1 again. And the next bits would be the ABCD values or the quantization interval values. And lastly, we have to reinsert 1 for the most significant truncated bit and enough zeros to complete our 12-bit code. So say for example, based on our given and the compression, say for example, we have this compressed code, and let me have this one as our sign bit again, and it belongs in segment 2, quantization interval. And now let's identify the 12-bit code based on this 8-bit compressed code. So first, again, copy the sign bit. Since we have the sign bit here as 1, copy it, followed by the segment identifier. Convert it first to a decimal system. So since this binary number is equals to 2, then we have to subtract it from 7 again. So 7 minus 2, that is 5. So again, in expansion, the answer of this subtraction would be the number of zeros. So 7 minus 5, that means we have to add 5 zeros. 1, 2, 3, 4, and 5. Next, based on the process I have presented or the algorithm, after the segment identifier, reinserting the zeros, we have to reinsert 1. So now this is the 1. This one here is the one that we have assumed or the one that we have dropped during compression. So this is the one again that is between our segment identifier and the quantization interval. So we have to reinsert 1. Next, the next 4 bits would be from our quantization interval. So we have to copy it as is again. So that would be 0, 1, 1, 0. And to complete the 12-bit code, we have to count how many bits do we have now. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. That means we have 1 bit that is lacking. To complete the 12-bit code, we have to reinsert the truncated bits. And for the most significant truncated bit, we have to reinsert 1. So that completes our 12-bit code. So we have 1, 5 zeros, 1 sign bit segment identifier, the one that we have assumed, the quantization interval, then the truncated bit. So we have to take note for the truncated bits. Say for example, we have 4 bits that are truncated. Or for a 12-bit code, we have 4 bits that are lacking. So I have stated that for the most significant bit for the truncated part, we have to reinsert 1. And the rest would be, we have to reinsert zeros. This would be the algorithm for the truncated bits, because if ever we have 4 bits that are truncated, our decoder would try to guess which number would that be, from 0, 0, 0, 0, For ones, it would try to guess what number would that truncated bits would be because they are just lost. So for the most logical guess would be the number or approximately the number between them. So that is 1000. So that would be for the truncated bits to minimize the error. So I think that would be all, and thank you for listening.